So thank you also for your kind presentation and okay. So in particular, I just want to introduce myself. I am, my background is in mathematics, and then I obtained my PhD in systems engineering, and currently I am a professor in automatic control in Sapienza. And these are my main research topics, and the question could be, what do they have in common with artificial intelligence? Because, okay, I have automatic control, optimal control, identification, modeling, image analysis. So what do they have in common with artificial intelligence? You will see during my presentation that almost in all the algorithms, almost all methods include one thing, minimizing a cost. So it means minimize the difference between the real data and your model of the experience, of the experiment, whatever. So, okay. These are the main words that I think you are familiar with. So words like artificial intelligence, machine learning, neural network. I'm sure that everybody used Gemini, ChatGPT, deep learning, layer perception, and many others. So I would like to show you what was behind all these words and some of these topics. In particular, we will talk about principal components analysis, classification, support vector machines. So I want to show you that behind some functions that you are allowed, that you are able to use, there is a lot of mathematics, but it will not be a lesson on mathematics, of course. So I will just show you, I will want you to be curious about all these topics. So to prepare this lecture has not been an easy task, because generally a course on artificial intelligence is about 12 credits in university. It means more than 100 hours. And also, each of these topics can be a course by itself. So I've made a choice. So I don't know if at the end of this lecture you will be more curious or disappointed. But anyway, I had to do a choice, and I want you to be, I don't know, just to see some of these methods. So if you need some of these algorithm, whatever, you know that they exist, so you can take a book, you take a paper, whatever, and you can go on. Okay, so let's start with some introduction. And if you go on the website, you write artificial intelligence, the first thing that you see is what is intelligence, what is artificial intelligence, and the history about artificial intelligence. And it is an easy task, because mainly the main results are from the last 20 years. But the origins of artificial intelligence can date back to, I don't know, 100 years. But let's go on. The motivations. About 20 years ago, 30 years ago, we were used to use computer just as an extension of our intelligence. So, for example, maybe you thought that the computers was able to do tasks that our intelligence was not able to do. For example, arrange 8 queens on a dashboard so that they are not able to capture each other. So it was a difficult task for us, and the computer can explore all the possibilities. But there are some tasks in which you can have computational problems. And so you go on with different methods, trial and error. So in some cases, it is not possible to explore all the possibilities. So you have to use some heuristics. And when I talk about heuristics to my students, they are not very happy, because they prefer formulas. But in artificial intelligence, heuristics are very common. There is also what is called weak artificial intelligence. So there are systems that can solve complex problems, but without capability of understanding. And then there is evolutionary computing, so algorithms that try to take inspiration from living beings. I want to show you just two slides to stress what is the difference between the possible standard approach to a problem and artificial intelligence problem. This is what I, for example, use, what I currently do when I work with my models. I work typically on epidemiological models. So I study the problem, the environment, the background. So I prepare a mathematical model, typically with differential equations. I compare my model with the real data, real system. So I have a model prediction, there is an error. So I can decide if this error is acceptable or not. And then by using optimization algorithm, so this is the first time I say gain optimization, I change my model parameters and go on up to the moment in which I say, okay, my model is what is called today a digital twin, a sort of twin of real data. This is the classical approach, and it works, of course. Another approach is the one from artificial intelligence. So totally different. They start from data, a lot of data. Then there are some methods. Here I post just the picture of a neuron. This is a confusion matrix and many other things that we will see today. And then you have the model prediction so that you get generalization capability. So if you use another data, you will probably have the model prediction of this data. So the question is the classical question: what is intelligence? What is artificial intelligence? Also in this case, we are used to say that there are a lot of kind of intelligence. For example, from school, you say you have a mathematical intelligence, spatial, musical, whatever. But if you want to generalize all this possible definition, we can say that intelligence is the ability to learn something, the ability to solve complex problems, to acquire capacity, to carry on abstract thinking. So artificial intelligence, here just put two definitions, is something that tries to simulate human thinking, human learning. And it is a nice definition here that artificial intelligence is something that does not work yet, because once it works, you can say that it is just software, which is totally different from the human behavior. Okay, so sometimes, just one slide to be funny, sometimes artificial intelligence has even anticipated what was in the artificial intelligence in movies, what is in science. I think that some of you is familiar with this kind of movies, Odyssey in the Space, Blade Runner, War Games, Matrix, something else, Mission Impossible. And I want to stress particularly this one, War Games, which is a very old movie. And at the end, there was a scene, there was a computer that was playing to learn something. So this is exactly the idea of artificial intelligence. So the computer that based on the experience, in that case, the experience was just an exercise, a very trivial exercise. It was able to learn something. Okay, let's go to the history of artificial intelligence. So we will understand some points, we will get some points. As I told you, if you go on the web, on some books, you will find many attempts to say that artificial intelligence was born, here, for example, with Erone of Alessandria that invented some automatic machines, or with Pascal, we invented the Pascaline kind of calculators. But let's go back to our time. I think that there are some key points. The first one, introduce the concept of communication between men and machines, is Wiener, with the concept of cybernetics. Today, cybernetics is sometimes referred to robotics or biomedical engineering, but at the very beginning, it was this, the communication between animals and computers. The first model of a neuron dates back to 1943 with McCulloch and Pitts that proposed the logical calculus of idea in nervous activities. So they try to mimic the action of a neuron. Then you will find a lot of data, and in particular, I want to stress this one, 1950, with Turing. We know everybody about Turing, the imitation game, and invented the Turing test. He wanted to verify the intelligence of a machine. The test was very easy. You can find different versions, but for the test is that you have a person on one room, and on the other room you have one person and a computer. And a machine is intelligent when you do questions and you are not able to recognize if the answer is from a machine or from the other person. But the two words, artificial intelligence, were introduced for the first time in 1956 during a workshop like this one. It was the first time in which artificial intelligence were two words put together by these 5 scientists, McCarthy, Minsky, Shannon, Newell, and Simon. From that moment on, there are different seasons, what are called first winter, then spring, again a new winter, and these different seasons depending on 2 factors. The hardware and software capabilities, so think to the computers of 1970, and to theoretical improvements. So some of the algorithms that you are used to use every day, backpropagation, learning, also the words learning, have not been introduced many, many years ago, but just during the last 2 or 3 decades. Another element that changed the history of artificial intelligence was also this one, the money, the funding, the governments that gave resources to this kind of research. So we have the first winter after a lot of optimism in the case 1970, 1980, because we had poor computational capabilities, more data set and not so many resources. Then a lot of optimism again. Then we have a second winter, because even if it was introduced the concept of convolutional neural network, and I will show you something about it, there was not enough computer power. So there were reduced funding, and the neural network were not so effective. Then from 1993 to 2011, there was increased computational powerful, and I think that you are very young, maybe you don't know these names, but in 1997, there was a computer, this Deep Blue of IBM, who won a chess match against the world champions of that period, Kasparov. So this is Kasparov, who was playing chess. And on the other side, there is a computer, this Deep Blue, and he won for the first time. Another play was won by this Watson, IBM, in 2011, because he won this strange TV quiz, Jeopardy. It is a quiz in which the TV presenter says a sentence, and you have to guess the question. So, for example, the sentence is, what happened in 2001? And the question is, the answer is the Twin Towers collapsed. And the question was, what happened in 2001? Okay. And so for the first time, this Watson, this computer here, won this quiz. So it had the capability of thinking, of using all the information all together. Then it is recent history. From 2011, there has been a lot of improvements. So the use of convolutional neural networks, CNN, that have been introduced in 1989, but now, 10 years ago, with computational improvements, we have been able to use them. Then improvements in computer vision, particularly the analysis with the images. It was a credible problem because of dimensions of the images. And then video games, of course, other plays, AlphaGo, this play, and improvements in speech recognition. We all use this kind of Google, Siri, and so on, but they depend on the fact that these systems are able to understand our voice. So also translation. Then autonomous car, medical image analysis. There are some applications that you take the picture of a small Nivo and it can say if it is dangerous or not, just because they have experienced it a lot, they have learned if it is dangerous or not based on some training algorithm. Okay, now in history, I mean, science history, there are what are called technological singularities. So sudden jumps in science. So it has been predicted that there will be a new jump, new singularity in 20 years, maybe before, but this is what has been predicted by these scientists. The singularity is near 20 years, but anyway. Okay, artificial intelligence includes many, many topics, and each of them should be. Okay. And each of them should be a course, okay? Robotics, machine learning, automatic programming, vision and speech, and so on. And the applications, as I said, are nowadays every day in home, medicine, fitness, also fitness. They can say what you have to do to get some result, self-driving cars, and so on. So it is important to fix some words, some concept once and for all. Because we talk about artificial intelligence, machine learning, what is the difference? So artificial intelligence is the big set. So there are computer actions that mimic human decision. So they take experience, and so they try to get the decisions. Then inside artificial intelligence, there is machine learning, just one part of artificial intelligence. And machine learning is the process that allows computer to draw conclusions. The important thing of machine learning is that it allows computer to learn outside programming. And we will talk about it during this lecture. Inside machine learning, we have deep learning. I have stressed the presence of deep learning because also for your application, they are particularly powerful. They are processes that allow computer to solve very complex problems. In particular, I will talk about convolutional neural networks. Among all these steps, machine learning is one of the most promising approaches because I think it stresses the three elements: learning, improving, evolving. During these lectures, whenever it is possible, I will talk about, I will talk in general, so not specifically about one or the other. But when I will focus on one of these three main topics, I will tell you. Okay, so let's go to data or pattern, and the process of learning. I want to stress immediately some of the basic elements of data analysis and learning, because I think that everybody has seen sometimes the neuron and so on, the back propagation, and we will talk also about them. But the methods, I think, should be the focus of this talk. Okay, data. As I show you in one of the first slides, data are the basic element with respect to the standard approach. We don't start from differential equations or relations, mathematical relations among things. We start from data. So data is, the definition is the opposite of chaos. Data can be everything. Data can be numerical data. So for example, if I'm referring to you, how much your height, your weight, the length of your foot or your finger, whatever. They can be categorical. So qualitative features, qualitative characteristics. I can define subject by means of sex, the color of eyes, the blood type, anything. And they can be sequence, so you can have a sequential pattern like video, stream, and so on. So when I talk about data without specifying, it is something like this. Okay, we have to learn from data. The process of learning, let's stop for example for a moment from the slides. If I have to learn something, from experience, from data, what can I do? I try, I see the result, I think it's acceptable. Okay, I try again, maybe I can do something better. When I see that my results are acceptable, I stop. So machine learning try to mimic this process. So the idea is that I have the data, I have a goal because I can do from this data many things, and then depending on my goal, I have to work, to try to learn from data. I can learn from raw data, so from the data as they are, or from features. Features is a word that we will use many times. You will meet this word a lot of times during an artificial intelligence course. Features are the characteristics of something. So features are, you have the data, so you can work directly for the data, or you can extract from the data special characteristics. Types of learning. If you want to learn something, you can apply your training just one time and then that's all. Or you can increment your learning by train again. So you do a lot of training sections. I don't know how many. Natural, so it is a continuous training section. Or reinforcement learning. This is the last way introduced a few years ago, applied in artificial intelligence, a sort of reward that you give to your network. You see, again, if you have a child and he has to learn something, he'll learn, and so you give him something, a reward, biscuit, something. So it's again the same applied in reinforcement learning. Okay, so this is the process that I was saying before. I have machine learning algorithm depending on some parameters, on some choice that I'm doing at the beginning. I have real data. I make a comparison between my system and my data depending on the goal. So I have an error. I have to reduce the error, so I update my parameters, and so on, up to what? Up to the moment in which I decide that my error is acceptable, or up to the moment in which I said, okay, my training lasts from 2 days, that's enough, or from, I don't know, 10 iterations, 1,000 iterations, that's enough, okay? So this is the process. You see, it mimics exactly the learning process that you apply every day, okay? When you have to learn a sport, you have to learn cooking, you have to learn something at school, at university, and so on. Okay, so the learning is this process here. I have a goal, I have an error, so I want to minimize the error, or I want to maximize my success. You see, maximize, minimize, they are optimization. This is the reason for which somebody with a background like me has been carried on in artificial intelligence. So the behavior of an algorithm depends on a set of parameters. The initial choice. So you have a cost index that defines if the difference between your goal and what you have obtained is acceptable or not. So this J of feed function of your initial parameters is something that you have to maximize if it represents the success, or you want to minimize if it represents the noise, the error. So the training phase is exactly this. I show to my system something, and my system has to minimize or maximize the objective function, the cost. So the problem is that you want to maximize or minimize something. If you ask to a students of school, what do you have to do if you want to minimize a function or maximize a function? It says, I do the derivatives, which is exactly what you apply in artificial intelligence. When you want to find the best parameters that minimize or maximize something, you do exactly derivatives with respect to the parameters that you want to optimize. Or if it is not possible to do the derivatives, and we will see there are many cases in which it is not possible, you use some heuristic methods. So trial and error, some numerical ways to do things, and so on. So the idea is very simple. You have this comparison, you have an error in this case, and you want to choose the parameters here so that the error is as low as possible. At the end of the training phase, you have a sort of machine so that you introduce new data, you have the output, that's all. So even if the training is very computationally expensive, at the end I will show you there are some cases in which the training can last days. Okay, even if it is computationally expensive, when you have finished, you have a sort of black box, a sort of machine. So you have input, output, that's all. Okay. Along with the parameter theta, you have also special parameters, what are called hyperparameters, that can be considered as special ones that you decide at the beginning, but they depend on you. Also, the choice of the loss function depends on you. If I want to minimize an error, well, it depends how I define the error. What is the error? I can write it in one way or the other. So depending on this loss function, on this cost, I found a different result. So which is the best cost loss function? I don't know. I decided at the end of my training algorithm. How can I set these hyperparameters? I cannot do derivatives because I cannot do the derivative of a cost function. How is it possible? But here I use heuristics. I fix at the beginning my hyperparameters with an initial guess. I just try. Then I found a result, and I put it on one side. Then I change my hyperparameters, I find my result, and so on, up to the moment in which I say, that's all. I use the best hyperparameters that perform the best result. Let's see. The central point in artificial intelligence are the data. So I divide the data into 3 sets. One set is the training. I use the data to do the derivatives, to find these theta parameters, and to find the optimal values of the parameters according to the special cost that I have chosen at the beginning. Then once I have found these parameters, I apply the validation. I apply the validation step on another set of data. So on another set of data, I will tune the hyperparameters. When I have finished, because I have finished my training sections, because I have decided that I can accept my result, my error, I apply my black box, my machine, my instrument, my device, to a new set of data that I have not used for the training and validation. If the result here is acceptable, because the error is small and anyway it's acceptable for my specific application, that's all. Otherwise, I have to go back. Probably I have to change something in the training algorithm, because as I will show you, we have a lot of possible algorithms. Maybe I will have to start from different hyperparameters, and so on, again and again. How can I split this data? The answer is, I don't know. Generally, in all the books, in all the papers, they suggest to divide the data into 70% training, 15% or 15%, or different percentage. But the idea is that they depend on data. They depend on how large is your set of data available for your training. I will show you, just to mention the difficulty sometimes in splitting your set of data in large sets. I will show you an heuristic method that can be useful when your training data is not large enough. The idea is this. You split your set into training data, all training data, and test set. Test set, you put it on one side. Then you divide your training data into some folder, for example, in this case, 5, 1, 2, 3, 4 sets, use it for training, and the last one for validation, and you do the test. Then you go back and you divide the training data into 5 folders, but you change the validation folder, you do the test and you find the result, and so on, up to the moment in which you use all the possibilities, and at the end, you choose the parameters and the hyperparameters that provide the best result in the test. You see, it is very simple, also very logical. It is something that I think everybody would have thought by itself. But it is an heuristic method with a lot of publications, supported by a lot of experiments, but it is what we are used to do in artificial intelligence. When you have not enough data to do this splitting, you have to do something. So you apply something like this, k-fold cross-validation. I've said many times, if the performance is acceptable, if the result is acceptable. What does it mean, acceptable? If I do a mistake of 1 meter is acceptable if I'm talking about kilometers, but if I'm talking about small distances, a meter is a lot. So it depends on the specific application. So the behavior of machine learning, it depends on some parameters, and we define some measures of the error. For example, the accuracy in classification, for example, it can be the ratio between the correctly classified pattern and the classified pattern. So this is very easy. You have to classify animals, and so you have done 5 good classification over 6. So 5 over 6 is a good result. There is another way to check if your results are acceptable. I think that maybe you have seen some of this, the confusion matrix somewhere. For example, if I have 5 classes and 5 classes, these 5 classes are the true ones, and these are the predicted ones. In the perfect world, I should have the results also only here. So it means that what are in class 1 have been predicted in class 1. What are in class 2 have been predicted as class 2, and so on. But sometimes I do some misclassification. So this confusion matrix indicates visually, and sometimes also using colors, indicates the percentage of cases in which you have done the right classification or the wrong classification. And as I will show you at the end of the presentation with a real application, it is also interesting because, for example, in this case, it means that, let me see, in this case, it means, let me see, okay, 15% of the classes that were in the 5 class have been classified as class 4. So I can go and check why my system have done this mistake. So sometimes they are useful also to yield some information. Other performance evaluations, for example, in binary classification, in binary classifiers are the ones that classify true positive, true negative, false positive, false negative. Everybody have seen some of these. You have to decide if something is positive or negative. So the false positive is when you have said something is positive and instead it is negative, and so on. So you have to define the rate of true positive, true negative, false positive, and false negative, and the total accuracy when you find how many times you have defined correctly positive, that is positive, and correctly negative when it is negative. There are a lot of metrics, and each paper that you find generally have to deal with this kind of ones, but sometimes they introduce also some other metrics. Two things that must be taken into account when you do training and validation and tests, and this is the problem of generalization. So I want my system to obtain the same accuracy also on the test set, and you have to avoid overfitting. So sometimes you train too well, and it is not a good thing because it seems that I have learned just on my training and validation data. so it is not good. A little mistake, a little error is acceptable, and also in this case I will show you why. I'm talking about learning. There are many kinds of learning. So here I show you just some boxes for methods, but there are many, many others, and each of them should require hours to explain. And for each of them, there are new papers every day because they stress training algorithm, then stressing training time. Sometimes some of them, they are very time consuming. So each of them require a lot of mathematics. And I will focus on some of these methods. Okay, starting from supervised learning. Supervised learning means that I have my data, my patterns that are labeled. So I have each data that has a label. It means, for example, I have an image. So I say this image of class A. Another image is of class B, and so on. I have a label. I know from the beginning to which set my data belongs. So the idea is that I have to learn a rule. The supervised learning can solve a lot of problems. In particular, I want to focus on classification and regression. Okay, classification is something that can give you class 1, 2, 3, 4, whatever, well defined. A class is a group of patterns with common properties. It can classify you with respect to some goal, for example, men, women, people with black hair, blonde hair, without hair, people high, tall, whatever. Depends on the goal. Classification is the idea of assign a class to a pattern, and it is necessary to learn functions that classify a subject to one class to the other. And the common algorithm, as I told you, are a lot, Bayes classifier and so on. And I will focus in particular on support vector machines and decision trees, but in particular on support vector machines because they are the functions that you will find on MATLAB, Python, and so on among the options. Sometimes we use MATLAB, for example, with the default options. When you go inside, they say choose among the different training algorithms. So among them, you will find all of this. So SVM, support vector machine, is one of the most common algorithms used to classify. Okay. Classification is obvious where you can find them. And okay, I want to start from an example and then I want to go deeper. Everybody has an email box. And if you go to the spam box, you find a lot of emails. Your system has been set, I hope from you, to decide whether an email is a spam or not. How? If I have to decide myself, I can say, well, it depends on the sender. If Costanzo sends me an email, probably it will not be in spam. But if somebody else sends an email, some sender sends me an email, sometimes yes or not. It depends if it has an attachment, if it has no text. So I have some criteria, but I must teach to my system to decide whether an email is a spam or not. So there are some features. The sender, you see, sender is not a numerical feature, is a categorical feature. Costanzo is good, somebody else is no good. Other features. So I have email 1, and my system has the feature Costanzo good, another feature the length, and so on, and the result is no spam. Email 2, and so on. So I have a lot of labeled email, so I know spam, no spam, depending on some features. So characteristics of the object. For example, in our case, the length, the attachment, the send, the spam, no spam, and so on. So how can I teach to my machine that an email is a spam or no spam? So if I have a new email, this yellow one, how can I decide whether it is read or green. How? Okay, let's go to the space of features. So here, I think just to two features because it was easy to put it on the plane. So the length and the attachment. So if the email is has low length and great attachment, I put it here. I just put on the Cartesian axis. So I understand that there is a difference between the emails, spam, no spam. But if I have an email here, can I say that it is spam? Probably yes. But I want to find a rule. I want something that I put in an automatic, so an email is spam, no spam. So let's start from the basics, from binary classification. I want to separate these two sets, so to classify these two sets. So I want to define in advance what is on one side spam, to the other side no spam. We are all mathematical people, so we say, okay, I define, okay, I need a straight line, this one, and straight line, this is the, sorry, this is the equation of a straight line. W1 x1 plus W2 x2 plus b equal to 0. The only problem, I know that the equation of a straight line is this one. So the only problem is that I have to find W1, W2, b. So the points on one side are with label +1, the other on the other side with label -1. So I can say that the points on this side has this quantity is larger than 0, the other quantity is less than 0. Mathematically, it is this. I'm looking for this hyperplane. I just want to talk with hyperplane. In this case, it is just a straight line. So that the points on this side applied, if I apply the function f, is +1. If I apply the function f to these points, is -1. So I have a mathematical problem. Which is the best separation hyperplane? Because here I put this line, but I can also put this one, which is right. I can also put this one, and so on. So I want, there's another one, no. So I want to find the best hyperplane that separates these two sets. Okay, so the logical idea is find the hyperplane that has the maximum, that sets the maximum distance between the points of one class to the points of the other class. This is logical. Again, maximum distance. I want to maximize, in this case, something. So I want to maximize the distance between classes. And support vectors are these points here. I'm not interested in the points that are very far. I want to maximize the distance between the points that are near my hyperplane. Mathematically, as I told you, there is a lot of mathematics behind this method. Mathematically, it can be shown that this W is the vector that is normal to the hyperplane. So I have to maximize this distance. So I want to stress the fact that the points of the support vector points must be with larger distance one between the other. Okay, so the factor vector machines maximize the margin, that is, maximize the distance between classes. It is easy, not difficult, to change one thing. Before I've written that this quantity must be larger than 0, this quantity is smaller than 0. Mathematically, it is easier for me to say larger than 1 and smaller than -1. It is not difficult. I put this one inside B, so mathematically it is easy. So the points on this side are the points with which this straight line is equal to 1. The points on the other straight line are the points with which this quantity is equal to -1. Just one slide of mathematics, because I want to stress the fact that these are not heuristics. Okay, I want to maximize the distance. The distance is something like this. The points here, x plus, the points here, x minus. The distance is this quantity, mu. So I can say that this quantity is proportional to my vector W, because I've said that this vector is normal to the hyperplane. So each point here, on this line here, x plus, are equal to the points here plus this distance. So plus lambda omega. Okay? So take this point here, this one. W transpose x plus plus b here. W transpose, instead of x plus, I put what is x plus b equal to 1. I do my calculation, just these simple calculations, and I find that this lambda, this proportional parameter, is equal to 2 over W transpose W. So here is it. My distance was defined as this. So my distance is 2 over the norm of W. So to maximize the margin, I have to minimize W, okay? So again, a minimization problem. Here it is. It is the classical Lagrangian problem that I think you have solved since the first course of mathematics. So find W and B that maximize the margin, so that minimize this, and such that if this quantity is larger than 1, you put the label, this quantity is larger than 1, if this quantity is plus 1, the label is plus 1. Otherwise, must be smaller than minus 1 if this quantity is minus 1. It seems it is just this. It is a mathematical problem optimization, very, very easy. You write the Lagrangian, you apply the condition, easy. What happens if I have these 2 points? So you see, you have a green point here on the side of the points red, the red point here on the side of the points green. I'm sure that some of you is thinking, I can cancel them, I don't care. No, mathematically, we don't do that. Here they are, this strange quadrant, cannot classify them. So I allow some misclassification. I introduce these slack variables, C, this distance, and I say, okay, do the classification as before, but minimize these points, please, the presence of these points. So my problem is I change my cost index with this penalty term. So the problem is exactly the same as before, but I accept some mistakes. So I don't just cancel these points, but I accept the presence of these points, but I ask you, please find a straight line that minimizes the misclassifications of these points. Okay, these are just mathematical hints. So if you need some more details, you know support vector machines and you find a lot of papers about these topics, but the mathematics that is behind is just optimization, just Lagrange problem. Okay, this is easy. I can put the straight line between these 2 points, but what happened in this case? Logically, for me, it is easy to separate these 2 systems. I just put here something like this, and I separated the 2 systems, but I cannot put a straight line. So again, what can I do? Think to this case. I have these points, easy. I can do the separation in this way, easy. What happens if the points are like this? How can I separate these points? You see, in this case, the separation is easy, straight line. In this case, I cannot do the separation. But the idea is very easy. If I introduce a function y equal to x squared, what happens? You see, the points change their values. So what was 4 becomes 16, and so on. So the points here that in this one dimension were not separated becomes separated in 2 dimensions. So now it is easy for me to say, well, this is my separation hyperplane. Okay? So the idea, you see, from this simple function, the idea is to do the same also here. I would like to do this. How can I teach to my system, to my machine learning system, to do this? Before I have introduced a function y equal to x squared. Now, let's say, I introduce Okay. I introduce what are called the kernel function. So I change from the two-dimensional space. I will go to a three-dimensional space so that I can put here a plane so that, for example, this is just an example, the points green becomes over hyperplanes, the points red becomes lower this hyperplane. There are also in this case a lot of paper to introduce separation, these kernel functions. For example, one of the most used is the Rayleigh basis function, this one, but it is not the only one because then you have to set the sigma, you have to sometimes introduce some other parameters to set this data. Okay, so also in this case, the basic idea is simple. Start from exactly, I want to separate point on a straight line. Okay? The nice thing is that you can implement all of this in MATLAB. So I use MATLAB and Python, but in MATLAB, you just have to load data set, you have input data, output data, and with this, just this simple function, you can apply the support vector machine. So you can separate sets, the input data, according to some options that you introduce, and so you are able to apply the support vector machines just by applying this function, because inside it implemented the algorithm that I have shown you. Pay attention that behind this simple function, there are a lot of options that if you don't apply, if you don't set by yourself, they use the default options. So probably they use the radial basis function or something already decided by default. So if you want to change something, if at the beginning it doesn't work, don't change immediately the method. Try to check the best option. Okay, let's go back to our machine learning supervised learning, and in particular, among the classification, when you know the label, so the supervised, we have also the decision tree. Just to slide to give you the idea of the decision tree. This method is loved by, in particular, the physicians, the doctors, because it is very logical. Also in this case, I'll show you with an example. I ask you, do you have fever? No, so you can go to school, to work, whatever. Yes. Then I do another question. Is it less than this grade? No, so call the doctor. I should go on with other questions. Otherwise, yes, so it is not fever, go to school. So you have a lot of trees, you have a lot of questions, and the right thing is that you have to do the right question, to be discriminant, to separate the sets, okay? So the trick is that the researcher must apply the best question to each of these nodes, okay, to each of these points. Also, in this case, there are some algorithms already trained on MATLAB, Python, and so on, but we need also you. It is you that put the right question somewhere. And this decision tree is very nice because sometimes a model is able to distinguish between two classes, but not between three. So by using correctly, in a smart way, the decision tree method, you're able also to distinguish between three or more classes. For example, I can distinguish between this class and the other two because for me they are confused, or between these two classes and this one because another method is able to do that. Then I put together these two methods and I have the ensemble learner. So I can distinguish between the three classes. You see, again, this is just heuristics, it's very logical. But it is exactly what is implemented in many MATLAB, Python, I know them, Mathematica, Maple, and so on. And so you are able to do classification with respect to as many classes as possible. This is very nice. The random forest has been introduced in 2001, especially used in this AdaBoost method. And the trick, as I told you before, is that at each node, you must choose the feature that best separate classes. So even if the methods are well implemented in, as I said, whatever, MATLAB, whatever, the researcher experience is required. Otherwise, you will not finish with your classification. Okay. Let's go for a moment to the regression. Regression is, again, a sort of classification, but without discrete values. Up to now, one thing could be in one class or the other. But sometimes it's not easy to do that. Sometimes I need a continuous evaluation of my prediction. Let's see. I have pattern of the training set. To each pattern, I have a label. The classical example in this case is I have a house of 40 square meters and it costs 100 of something. I have a house with 100 square meters and it costs 1 million. If I have a house of a price inside these two quantities, how much should be the right price? I don't know, because the price of a house depends on a lot of factors. Depends on if you have buses, if you have schools, many things, many characteristics. So the idea is that I want to find a relation that connects the input to the output, that I'll teach to my system to assign the right values. So mathematically, I want to find a function f that associated to specific pattern, the label. The label that can be a continuous value. So let's see. Okay. So if we are talking about linear regression, I need to know A and B. Epsilon is some noise. So what do I have to do? I have to minimize the difference between my output, the price of the house, and the model that I have, a simple least square problem, a very simple least square problem. Let's see how. I have some data, the first data X associated with this one. Think to square meters, the cost of the house, square meter, the cost of the house, and so on. I want to find this straight line that allows me to say if the cost of the house is here, and which I don't have any prediction, any idea, which should be the best cost of the house? The solution is again obtained by using the derivatives. I have to solve the least square problem just by minimizing the error. Let's see. Okay. This is an example. So what happens if I have these two quantities not considered here? I find the linear regression curve. And so I can say, well, if I have a house of 60 square meters, the right price should be this one. The right price should be this one, and so on. Okay, so this is a linear square regression. You see, I don't have a class. I don't have class 1, 2, 3. I have just an estimation, the best estimation that I can introduce just by starting from experience. Pay attention. You can have the problem of underfitting depending on the data. If the problem is too simple, linear regression is not good in this case. This is not a good fitting. But I could have also the problem of overfitting. In this case, I will not find a good regression. This is not a linear regression. That is not a good one. But more interesting is the multilinear regression. So for example, for the price of the house, I can think to the house age, to the area, the population, the characteristic of my neighbor, and so on. So mathematically, I can have something like this. So I can have a lot of data with a lot of characteristics. This is my output, so the price of my house. So I want to find the relation between X and Y. So I want to find something like this. So I have to evaluate this beta, so these n parameters. Again, a simple problem of minimization. that can yield your solution with this formula. If you take one of the book of identification, you find this formula. But again, you can have mathematical problem. Attention, in the case of conditional matrix, I have to say this as a professor, I still have these things. Okay, also in this case, you have to evaluate the accuracy of prediction. So for example, the mean square error, the mean absolute error, the mean absolute percentage error, any metric that can measure how good is your prediction. Okay, let's go to the unsupervised learning. This is very nice because in this case, you don't have labeled data. Let's see. Classes are not known, the data are not labeled. The problem is that I have a lot of data, for example, here, and I have to cluster them. So I have to group them according to some characteristics. Okay, to some characteristics. I can group them according to the color? No, because the color is the same. I can group them according to the dimension? No, the dimension is the same. So maybe I can group them according to the fact that some of them are nearer with respect to the other. So I can say, okay, maybe they are together with respect to this characteristic. Also grouping, also clustering depends on the way in which I do that. This seems very logical. I put the pen and I do this. But depending on what you mean, you can clustering your data in different ways. For example, this is the minimization with respect to centroid. So I have the centroid, so the average of all the values of these points. You minimize this quantity, and so you have the cluster 1 and cluster 2. And this is a good criterion if you have radial symmetry, so you see almost a circle. But if you change the system, if you change the cost index, and you want, for example, to minimize the distance intra-classes, you have different results. For example, if you have these quantities, according to me, well, there are 4 groups. First of all, why 4? Who says that there are 4? First, the second thing is I can group them this way, I can group them this way. That depends on whether, that depends on the choice that I put here of the definition of the distance between my centroid and my points, or between the classes. Also, the decision of how many classes there are depends on the criterion, depends on what I want to do. I can classify this audience, with respect to 2 classes. So I think men and women, but they can be also between, as I said before, black hair, blonde hair, the weight, the eye, and so on, depending on the criteria. So this is exactly the same. Okay. So clustering, you can see many algorithms, and in particular, I want to show you the clustering with respect to centroid, and in particular, k-means. You see, when I said at the beginning, I had to do some choice with this lecture because all this topic is a lesson by itself, okay? So the k-means, this is a rigid method. It is a method for which 1 point, 1 element can belong to one and only one cluster. So you cannot have, as before, a point that is either here or there. The optimization process is iterative and local, and the problem is you can attain local maximum. All the time that I say you maximize something, you minimize something, I would like to find the optimal values. It means the global minimum or the global maximum, which is the maximum with respect to all the set of data you have, all the possibilities you have. But sometimes I'm not able to do that. Sometimes I must accept to find only local minimum or local maximum. So let's see how it works. First, how many clusters do you have here? The choice of the number of clusters, if it is not given in advance by somebody, is a tough decision. So there is an heuristic. You find, you have here the number of clusters, here the cost index. So depending on the number of clusters, you have a different value of the cost index. So for example, if you choose just 2 clusters, you have this value, 3 classes is value, 4 classes is 1, and so on. Well, there is an heuristic that says the value, the right value, the best value should be the one in which your cost index change its slope. You see, it starts in this way and then change its slope. With this picture, it is very easy, but sometimes you don't have these very clear slopes, okay? So, as I told you before, I would like to give you some formulas, but sometimes it is not possible. So, the heuristic that is usually applied is this one. When there is a clear change of slope, okay, this is the right number of clusters. So let's go back to my example. Assume that the right number of clusters is just 2. Then you initialize the centroids. So I say that there are 2 clusters, and I put, using some heuristic or just trying, the 2 centroids, one here and one here. Okay. Then I assign the points to one of the clusters, measuring the distance, for example, just an example, the Euclidean distance to each of the centroids. So, for example, this one is very near to this centroid, this one is nearer to this one, and so on. Then the centroids are updated by evaluating the average of the point assigned to each cluster. You see, the centroid was before. Then I update my centroid, trying to find another point in which, for which the distance is smaller with respect to the other one. And go on. You repeat these steps 3 and 4 up to the maximum number of iterations that you are allowed, or up to the moment in which the position of the centroid don't change anymore. You see, again, there are heuristics. I stop after 10 iterations, 5 iterations. I'm trying, okay? Now, in the part of machine learning without labeled data, there is an important chapter. I want to stress this because it is really important. The dimension reduction and the feature selection. Nowadays, we have a lot of data, too much data, too many sets of data, sometimes, many times not labeled, and we need to decide which of the data is more interesting for our purpose. The principal techniques to reduce dimensionalities are these ones. These are the techniques that I usually use, but the one that I liked a lot is this one, the principal component analysis. I liked this method because it has a lot of potentialities, and all the time that I use this method, I think to another one. Let's see. The goal of the principal component analysis is to extract relevant information from a data set redundant and noisy. When I say relevant information, I mean this. Just an example. When I do my lectures in class with my students, I start with lecture 1. Lecture 2 is, with lecture 2, there is an overlapping because I have to repeat something from a previous lecture. Lecture 3, there is a little overlapping because I want to repeat something. So the relevant information is not exactly lecture 2. It's lecture 2 without the overlapping with lecture 1. So principal component analysis is able to extract the relevant information without avoiding redundancy, avoiding things that have information repeated from one data to the other. So they want to reduce redundancy and maximize information. For example, if you see this, you see 9 squares, 9 yellow squares. If I ask you to describe this, you say, well, I have 9 yellow squares put in an ordered way, that's all. If you see this data from this picture from a different point of view, you find this. So you find a 3-dimensional data. okay? Principal component analysis is able to also to do that, also to show you the data from a different point of view, so that you are able to extract the best information, the most important information you need. Okay, so feature selection, dimension reduction. Let's see. You have a lot of cats. I want to define each cat with two characteristics. For example, the length and the breadth, which means this. So this is something very logic. I can collect the length of each cat, and probably this is the relation between the length and the breadth. So some data. I don't expect to have a very long cat with very, very thin. Probably there is a relation among them. So I ask, does a relation exist between the two measures? Second question, is it possible to find a unique parameter? So if I define the size of a cat, can I say just one number? 5. Does this number define the size of a cat? This is an example, and the answer is no. But in general, probably I can find a unique number that can define the measure of something. The idea is this. This is my graph of length, breadth. Well, I choose a new set of data, new axis, centered in my set of data, and then I rotate it. What is the advantage of this mathematical operation? The advantage is that I can see my data from this point of view, so minimum variance, because from here I understand that while the lengths change a lot, the other dimension changes in different ways, but I'm not able to get which is more important than the other. So in this way, I cannot say that one dimension is more important than the other, but I stress that the fact that in this direction, the data are not changing a lot. Instead, from this direction, the data are changing a lot, maximum variance. So you see that if I'm here, I see a lot of things. If I'm here, I see data changing not too much. So maybe I can define a new measure. The new measure given by one coefficient multiplied by the length plus the other coefficient multiplied by the breadth. This means that I have done a reduction of data dimension. So the problem is find the right ways to do that. You cannot do just 5, 0.9, which is the right weight. Okay, so you evaluate the correlation matrix of the data. You evaluate its eigenvalues. For example, 1.5, 0.8, I just invented this number. And then the weights, W1, W2, are the eigenvectors of the correlation matrix. You see, they are the lengths of the semi-axis of this ellipse. So mathematically, it's very easy what happened. I started from this data. They are right data. I have collected a lot of cats. I've measured the length, the breadth. They are right. But this data, which for sure are correlated, because as I said at the beginning, it is not possible to have a cat with very high height and very low, very high breadth and low length and vice versa. So it is obvious that there is a relation. But in this way, with this change of coordinates, so new axis and a rotation, for me it is possible to see something that from here it has not been possible. For example, in this case, I have the two eigenvalues. I put here in decreasing order, lambda 1, lambda 2. This is my the matrix of weights found as the eigenvectors weight. So I have two principal components. W1, Y1, W11 multiplied by feature 1 plus W21 multiplied feature 2. The principal component Y1, so if I just use Y1 as the measure, has preserved about this quantity of the original variability, of the original information. So if I go on just with this Y1, it is not enough. I'm not taking into account everything. But anyway, I have just one number that preserves about 65% of the information. Okay? So the procedure is very easy and can be applied when you have a lot of data and a lot of features. For example, in this case, I have n data, n measures, n cats. You have p features, the breadth, the weight, the length of the ears, I don't know, many things. So you need to find a suitable combination of the p variables, of the p features, such that the information that you get is more informative, okay? It is not important that the cat has the length of the cat, the ears cat is 2, 5 centimeters, whatever, or the weight, but I collect them all, and so I have a unique measure, or two more measures, such that they get the most relevant information. The procedure, here I put everything, you have the data set, you measure, you find the covariance matrix of the data set, or the correlation matrix. It depends on whether the data are the same degree of, depends on the variability of the data. Then you evaluate the eigenvalues and you put them in a matrix in an ordered way. Then you find the corresponding eigenvectors. So you have the matrix W. And so this is your transformation, Z equal to X multiplied by W. So you find a new transformation, the equivalence of this transformation here, so that your data are available in a different way, in a more fashion way, okay? Here is another example. I generated these two signals. I found the covariance matrix. This is the correlation matrix. You see, it means that the correlation between signal 1 and sigma 2 is about 20%. It means that in the signal, about 20% of the information of signal 1 is contained in signal 2. So since for me it's a problem to carry on all the information given by all the data, I want to reduce this information. Also because, not only because I have problems with my computer, but also because I want to see things better, okay? So it is important to reduce the redundancy. So I write the matrix of eigenvalues, I find the eigenvectors, and here is my transformation matrix. So it allows to observe data in the direction of maximum variance. It is exactly the situation in which I see my data from here, from this point of view, okay? This is the best thing to see everything. Okay. Also, in this case, I always talk about MATLAB because it's something that I use, but these functions are implemented also in other with other software like Python for sure. So you have just with this function, depending on whether you use the available data or directly the directly available data or the covariance matrix, you have immediately all the information, the matrix of eigenvectors, the weights, the eigenvalues, whatever you want. Here you can add many things. So the data transformed and the eigenvalues, depending on what you put here, you have all the information about the principal component analysis. Okay. Now, this part is, from some point of view, easy for you, and from others, I hope, very, very interesting. Okay. As I told you at the beginning, in 1943, these two scientists introduced the first neurons model. It is a very nice paper. If you want, you can find it on the web. And I think everybody has seen a picture like this. So you have some inputs, you have some weights. Here you produce a linear combination of these inputs and data. This one. then you don't use directly this linear combination. Maybe yes, maybe not, depending on this activation function, and you have the output. So the output is just the function f, the activation function f, applied to this linear combination of data plus this bias, which is a useful value that sets the set point of the neuron. And the activation function is a nonlinear function, continuous, differentiable almost everywhere, because you need it for some mathematical operation that we will see in a moment. I want to stress the fact that here you have a linear combination of data, but here you have to introduce a nonlinear function, because usually the relation among data is not linear. So if I just want to go on with the data as they are, it is a problem. I'm not be able to use nonlinear data, real nonlinear data. So usually an artificial neural network is composed by a lot of these layers. You have inputs, output, and inside a lot of hidden layers, 1, 2, 3, up to hundreds of layers. And you can go from input to output in different way. For example, with a feed forward, so the connections are only on these directions, connects neurons only from left to right, or also in a different way. Let's see what does it mean, all of this. The function, the neuron Z1 is equal to the linear combination of what happened before. Let's go directly to the example so we understand immediately. For example, Y1 is equal to the activation function F1, so W11 multiplied x1 plus W21 multiplied x2. And so on, W4, let's go to Y4, it is this, and so on. So it is very easy, the concept of neural network, a linear combination of the input with some weights, and then you apply an activation function. So the problem, I see, if I have a student have to study these things, I see many kinds of problems, but in particular two. These weights, who is able to yield these weights, first of all? Then what kind of function f do I have to choose? And then there are also other questions. So how many layers? What about the bias? And so a lot of problems. So you see that even if the concept is easy, the decision of how to go on is difficult. There is also another way of, there are also other network, for example, the feedback, so called also recurrent neural network, so in which it is possible to use the information get from the output to the input. In some nodes, in some neurons yes, in some others not. So sometimes you have seen the multi-layer perceptron introduced in 1956, in which the activation function is a step function, another nonlinear function, very peculiar. It is not a sigmoid. In fact, the success of this multi-layer perceptron depending on the specific application. The output of this point can be written in this way. I need this notation for the next slide. So this is the reason for which I introduced this notation. So linear combination of the input plus the bias. Once fixed the topology, so it means the structure, the input are given. Once fixed the number of layers, the number of levels of neurons, and so on, I need to find the weights that are able to map the input to the output. And this mapping depends on the specific application. So how can I find this weight? The answer is obvious. About in 1985, it has been introduced the error backpropagation. 1986, the error backpropagation. The concept is obvious. I have all these layers. I have the output. Do you like this output? It depends. I evaluate the error, so the difference between the output of my net with respect to my goal. So I do the update of the weights so that I want to reduce this error. This is exactly the problem, to find the weights, and one way is to use the back propagation. So how can you update the weight? I think that after these almost 2 hours, you know. You find the weight so that you reduce the error. Again, this is my loss function. This loss function is equal to the error, so 1/2, because it is easier to do the derivatives with 1/2. You just simplify these two. The number of classes, you have the difference between the desired output and the output of the net. Pay attention, also the output of the net depends on the weight. So I have to find this weight, and how can I do that? Just by doing the derivatives, again as before. The derivative, because I want to move in the direction of the decreasing gradient. So again, the second slide with some formulas, just to show you that the mathematics is very easy. I want to do the derivative of J with respect to W, the weight W JK. So the derivative of this, I simplify the two, only ZK depends on the weight. I use the color to help you. ZK is given by this, the activation function applied to the output of the net. Then I use the composition of the derivatives. I get to this point. I call this quantity delta K just because I want to put a name. And so my derivative of the cost index with respect to weight is equal to this quantity that is well known, multiplied by Yj, that is well known too. So I have my update given in this way. So I start my artificial neural network with an initial guess. My weight, I put my weight equal to 1. It's okay. Then I apply my system and I update my weight in this way with this update, delta Kyj, multiplied by a coefficient. This coefficient is a learning rate, and it's up to you to fix this learning rate. If you fix this learning rate too big, very large, you will have a lot of oscillations. If it is too small, you will never get to the solution. So again, some heuristics, it depends on your experience. You start with small values, then you increase, and you will get the right learning rate. In the training, you have some words that is better to learn immediately. Epoch, it refers to one complete pass of the entire training phase, to the entire training data set through the learning algorithm. So sometimes you have to set, sometimes always, you have to set your epochs, and the iteration indicates the number of times that the algorithm parameters are updated. Also, these parameters must be set by you. If you don't set this parameter, the system will do it for you. So if your system does not work immediately, change, go to the options and change. For the activation functions, generally you have the tangent or the sigmoid. Very nice is the softmax. Remember this, because at the end, in one application, I will use the softmax. Okay. We can stop this. Sometimes it's not enough to use the learning rate, the very small, very large, and so on. Sometimes you need some regularization. And because you want to reduce overfitting, and you want to stress generalization capabilities. Again, some heuristics. So this is your cost index. You have to add something. For example, this. So you want to reduce the dimension of the weight, the values of the weights. So you introduce some penalty terms. Okay. Sometimes it's not even enough. You have to introduce another parameter. You see a lot of heuristics. This is your update, but if it is not enough, you have to introduce another parameter, the momentum. So you have the update of your weight, the weight of before, plus the update that we have seen up to now with the derivatives of the weight. But if it is not enough, sometimes you have to add the momentum. Without the momentum, you can have these oscillations. With the momentum, you can reduce these oscillations. Regarding these tricks, there are a lot of papers. Sometimes you don't find these tricks in the books. You find them directly in the papers, okay? Because they are tricks introduced a few years ago, okay? And sometimes there is not a rule. I cannot say use the momentum like 0.5. I don't know, okay? Among the inside the machine learning, as I showed you at the beginning, there is a very nice and recent chapter, the deep learning, the deep neural network. The deep neural network are the neural networks that we have seen up to now, but they are deep because you have a lot of hidden layers. Here you say up to 50, but there are some layers even with a larger number of hidden layers. So the characteristics is the number of neurons, a lot of connections, and the weight. Here, just to show you some example of complexity. See this, AlexNet, introduced more or less 10 years ago, has about 60,000 parameters. 60,000 parameters to be set, and it is an old net. This VGG, Visual Geometry Group, because it has been introduced by this group, it has 60 levels, so not so many levels, but you see 50 million neurons, okay? So the ability of you, of the researchers that have to use this net, is to set things so that your system will not stay hundreds of days to be trained, okay? Then there is this ResNet that we used recently. Okay, let's see deep neural networks. I like them a lot because they are really powerful. Okay, among the deep neural network, you can find the convolutional neural network, the recurrent neural network, used in particular for natural language, hierarchical temporal memory network, and so on. And in particular, the convolutional neural network. You see, we are going deeper and deeper because, as I told you many times, each of these topics is a book or 10 papers, okay? Convolutional neural network. They were introduced for the first time for computer vision. Think that for computer vision, we had a lot of problems because images, think to an image, to a photo, it is very heavy. So the elaboration of each photo is computationally expensive. Think to a video, the computation of the numerical computation of each video is really expensive. And think to the extraction of information from a video. So it's a problem. So it was important to introduce something that was very easy to be implemented. Let's go to the definition. Just definition, convolution. You know what is a convolution. Mathematical is this. What I need to do is a convolution between objects. So I have the input, for example, it is something like this. You have numbers. These are my neurons. Then I introduce a filter, and I want to do the convolution between these two objects. The convolution means this. 1 multiplied by 0 plus 2 multiplied by 1, and so on. So I substitute these 9 numbers just with this 6. So I have reduced the dimensionality of my initial big matrix with this just one matrix, one number. This convolution can be done in all these, I call it image, but in all these matrices in many different ways. For example, the next convolution is where I have to jump one step, 2 steps, 3 steps. I have to do some overlapping. Well, it is your choice. So depending on this convolution, you will stress in the image, in the matrix, one aspect with respect to the other, just to show you. This is an image that I think you have seen many times, a spaceman. If I do the convolution with a matrix 1 by 2, this is value 1 and this is -1. MATLAB put white when you to the to 1 and black to -1. So when you do this convolution, so I apply this operation here, I find this. You see, I have cancelled some elements, I have stressed some others, I have lost the information about the color, because this was red and this was gray, everything is gray, but I have stressed the edge. If I do the convolution with +1, -1, +1, -1, I find something else. I have probably blurred a little bit my image, and I have stressed some other element. So when you apply the convolution to your matrix here, depending on the specific kernel that you use here, you can stress one element with respect to the other. You can stress the color, the edge, one kind of feature, remember the characteristic of your data, whatever you need. Okay. You can do the convolution also in 3 dimensions. So this is my kernel of before, my little matrix of before, and this is my depth that can represent the features map. So imagine that you have your image with all the features, everything, and you do the convolution with something that will stress one aspect with respect to the other, okay? And so on and so on. So you do this convolution, not one time, but many, many times. And then you collect together the information given by these convolutions. So in the convolutional neural network, you do the convolution, each of them with a convolutional filter, a series of convolutional filters. Each of them activate specific features in the image. Then I have to apply the activation function as before, because the convolutional neural network are exactly the same as before. The only thing is that they have these filters, and the only thing is that they have a lot of layers. That's all. For the activation function, well, the sigmoid is not good because the sigmoid reduces the weights. Since you have to do a lot of iterations, sometimes you will have the problem of vanishing gradient. So it has been introduced the ReLU, rectified linear function, activation function. Remember, before I said I have to introduce non-linearities. Well, this is not non-linear function because it is 0 and then the same function. So it is non-linear, but it is not a lot, an heavy non-linear function. Then the last step is the pooling. I said at the beginning that I can have 60 million of neurons, a lot of features, and so on. So I want to reduce, again, the dimension of my data. I want to reduce the dimension of my data without losing information as much as possible. So there is this operation. I want to show you with an example. Assume that I have an operator max, and I use a 2x2 filter with stride 2. So I have 4, 4, 4, 4 numbers. Just with this information, I know that. Consider the first 2x2 square. Who is the maximum value? 8. 8. Then 0, 8, 1, 2. Which is the largest value? 8. Here 3, here 6. So I have reduced the dimension of my square here in this way. Of course, I have lost information, obvious, but I have reduced the dimension. And depending on you can choose different pooling operators. The most used are the maximum and the average. I use the average many times. It depends on the kind of data that you have. So your net, the single layer, is composed by the convolution, that strange operation that we did before, plus the activation function, this ReLU, plus pooling. So each layer is composed by this. So you do it many times, 50 times, the most common about 50, 70 times, but also more times. When you have finished, because you have set the number of layers, when you have finished, you apply the classification, the final part. Classification in particular, but you can do just the final step, which is the comparison between the output of your net, the output of all of this, and your goal. The last steps are composed of fully connected layer and one of the methods that we have seen before. For example, the support vector machines. So the last step is the fully connected layer. I just put an example. It means that every neuron is connected with every neuron in the preceding layer. It is a sort of, I want to use all the information I get at the end of my procedure. For example, here you have the input, you have the weight matrix, you do the operation, so you obtain a 1/2 output in which you have used everything that you have obtained in the last layers, okay? So this is your procedure, the procedure used for training. You start from the data, convolution, ReLU, pooling, convolution, ReLU, pooling, and so on, many times. This is an example of one of the nets that I used recently. I started here, then convolution, ReLU, pooling. Another step, this is done by MATLAB. I didn't do this. I just set the number of layers, I just set the function, and then it does everything by itself. The problem of training is that it can require days. At the beginning of about 20 years ago, when I started to work with this, we have to do all the steps by ourselves. So find the features, do the training. All the time I asked, it's not here, I asked Vittorio, I need more images, more data, and so on. Because you have to start every time from the beginning with training. Now, once the CNN is trained, it can be used for similar problems. So you have a lot of database of functions already pre-trained. So if I have to use, to classify, for example, images of spacements, as we did together with Costanzo, I didn't start from zero. I used a pre-trained network already trained on set of images. It was not trained on a set of images that I was using with Costanza, otherwise, where is my work? But this net was trained to find features. So it was used to find edges, to find colors, all the possible features that you can imagine in an image. So it started from something already consolidated, okay? So if I have to classify photos, okay, my algorithm is already used to classify with respect to the shape, to respect to the edges, to respect to the colors, and so on. So it is a great advantage because you don't have to start, when you have a new problem, you have to start from the beginning. I want to show you a recent application. I think that also Costanzo will show something similar, but from a different point of view. Inside this project, done with the University of Cassino and some other of University of Rome, we have to define a model able to predict the mechanical behavior of additive manufacture of components starting from the knowledge of the microstructure and the process-induced effects. From my point of view, I'm not a metallurgistic researcher, just work on data. From my point of view, I had to classify images depending on the way with which they obtain these images. they obtained these images using some parameters, 8 classes. So I had to classify the images with respect to these 8 classes. So this is the dataset creation and pre-processing. So they have done all the possible analysis on this data. So I had the 8 different classes. In some cases, the difference is obvious, but in some classes, the difference is not so easy to be checked. Okay, so first of all, the data were a lot, but not too much. So I had to do data augmentation. In this case, the physics was useful for me. They said, I don't care if you rotate the image because the mechanical properties are the same. I don't care if you mirror the images because the mechanical properties were the same. So it was possible for me to do this kind of data augmentation, no problem. Then I apply what I said before, the convolutional neural networks. So the convolutional stage, you see, I found from each convolutional stage a set of different features. This is just an example of features I obtained. I use the activation stage. In that case, I use the maximum, this one, and then the pooling to reduce the dimension. And I did it many, many, many times. And then there is also the last step, the fully connected layers. For the result, we divided the set of data into training validation set, test set, and I used this ResNet 18, which is a pre-trained network followed by a support vector machine with multi-class classifier. Now you know something about this method. This ResNet 18, it is a pre-trained network specifically for image analysis. So you go to MATLAB, you say, you ask which is the best net for image analysis classification, and you find this one. Now, after 1 year, it is obsolete function. There are other functions, but there is this one. Then I have to do the classification, and since I know support vector machine, I prefer this one. I have tried also some other, the shuffle net, but it didn't work very well. So I found this confusion matrix. Now you know what is a confusion matrix. For example, the image what was in set 4 was correctly classified 32 times, but wrongly classified as set 3 13 times. So I said, why? What is the problem? Did I do a bad job? Well, I see that they are not very different, and most of all, the parameters, the production parameters with which set 4 and set 3 were obtained were similar. So it was a mistake, okay, sorry, but it was not a very big mistake because it is motivated by the fact that these two classes of images were obtained in the same way. As I said, I use also the shuffle net that at the end, in the last step of the net, do a shuffle of the features of data, just to use again everything. And here is in this case, I want to show you the loss function, the cost function, that it goes to about 18.5%. And this is, sorry, the accuracy. And the loss function, the cost function should go to 0. Instead, it goes about to 5%. So not very, very good, but we can accept it. Okay, the last part is, I think everybody's familiar with these problems of artificial intelligence. We have a lot of problems due to legal aspect. So, for example, properties about privacy violation, mathematical problems due to the bias that we can introduce in artificial intelligence. Sometimes there is a bias in the data collection. If I collect data, for example, in this room, I can say that the population is mostly of men, which is not true. So depending on the kind of data I collect, I can have also this bias. The need of integrating artificial intelligence with existing systems. When you want to do autonomous driving, you cannot cancel everything else. So you have to in some way integrate artificial intelligence method with what already exists. Then the computer power. As I told you, there are papers, everyday papers about to improve the computational capability and also methods. So all the time you have software, hardware improvements and methods improvements. So they go together. And data privacy and security. Also, some legal issues are still evolving, like intellectual property. Sometimes you use, as I said, pre-trained network. So what is new and what is not new? What is mine and what belongs to some other people? Then transparency, because people is not used to know what is behind artificial intelligence, so it is important to make this method known to have consciousness of these methods. And then, of course, possible cyber attacks. As I told you at the beginning, maybe from this lecture you expected something else. Maybe you are disappointed because you wanted to see something different. But as I told you many times, artificial intelligence, the fundamentals of artificial intelligence should be a course of more or less 120 hours. So, of course, I could not show you everything. The idea was just to give you some hints to make you curious about this method. So, for the references, you see some books, but most of all, I suggest you to attend some courses. There are some very nice courses, videos. So if you want to go deeper to some specific aspect, of course, for example, support vector machines, they have been introduced a few years ago. Now you have some papers and books on support vector machines. But if you want to have an overview, if you have an idea, to go deeper to some of these aspects, I suggest you to see to attend some courses. So also some very nice courses from some colleagues, this is from Bologna, this one's also with a lot of examples. So I suggest to check some of these websites. Finally, thank you.